Morning, everyone. All right. Can you hear me all right? I think the class is fine. If people on Zoom can also let us know if you can hear us all right. There were some sound issues in the previous recording, so we're just monitoring that as well. So welcome to another Data 100 lecture. This is our first lecture after the midterm. We are still grading your midterms, and we should be able to release grades later this week. So it's still in progress. So it's there's going to be more information coming your way through Ed, and some emails that we'll be sending you later this week. Grad project is also released. So for those who are enrolled in 200, 200S, 200A, please make sure that you check the announcement about grad project and get us started on that as soon as possible, because the group formation and the project proposal is due this Friday. There is a very short turnaround time because we just want you to be able to form teams and let us know if you have issues and you need help in forming groups and finding partners for your groups as well. So let's dive right into things. This is our lecture 16. We canceled the previous lecture, so we skipped that lecture numbering there. And today we're going to talk about cross-validation and regularization. So specifically, this lecture is divided into two different pieces. So in the first half of the lecture, I'm going to talk about cross-validation and the idea that during the training process, we might need to have different segments of the data to do different things, to do training or to do some kind of validation and to test the performance of the model on some kind of data set that we'll treat it as unseen data that we have. In the second half of the lecture, I'm going to talk a little bit about how to control model complexity. And in terms of kind of motivating what I meant by having different segments in the data, I want to start by talking about the two kind of lingering questions that we had in lecture 14. Remember, in lecture 14, it was a feature engineering lecture. It sounds like a long time ago that we had that lecture, but technically, those two lingering questions were the idea that we kept saying that there is unseen data set that we need to make sure that our model is performing comparably well on the unseen data set, as well as a good performance on the training data. So today we're going to take a look at what do we mean by that and how can we simulate some set of data points that we can treat that set of data points as unseen data sets in our training pipeline. The second part of, or the second question that we started kind of discussing, but we didn't entirely answer it, was the idea of the model complexity. In the model complexity issue, we were saying that if we keep adding features and if we keep increasing the complexity of the model, then there is the issue that the training error is going to decrease, but then the variance is going to increase. So we wanted to find out what is the sweet spot at the point that the model is not underfitting, it's not overfitting, so we can kind of have a sense of whether the model is going to have a good performance or generalizability capability on the set of unseen data points that it has not observed before. So the first half of the lecture, the first 30 seconds, I'm going to basically talk about how we're going to measure models' effectiveness or models' performance on the unseen data and what I mean by that. And then in the next part, I'm going to talk about how to find this exact sweet spot. In the middle where we have a reasonable performance on the training data, but it's still the model variance is not as high. So that's where we're going to talk about cross-validation, how to evaluate models' performance using different segments of the data in our data set that we're creating ourselves. And then the second half is called regularization, which is the idea of how can we regularize or control the model complexity so that the model is not overfitting to the training data and is not going to exponentially get complex and fit exactly to the pattern of the training data without any generalizability to the unseen data that it can observe. This was a nice plot in the feature engineering lecture, and this is kind of motivating why we keep talking about unseen data. If I were to give you only 5 data points, and I would tell you that, okay, go ahead and use these 5 data points in order to fit a model, and then say, for example, this is a polynomial function that we're, or a polynomial model that we're fitting with like degree of 4 or 5. we saw that if we keep increasing the model complexity at a certain point, the model is going to be able to fit exactly to the data that we have. So in this case, the error of the model is going to be close to zero. So mean squared error is going to be exactly equal to zero because the model is exactly passing through all of the data points and matching all of those values. But if this sample of 5 data points was a sample of a larger distribution, and you see on the right the original distribution of the data, so in that case, you're seeing that the model that we came up with using only those 5 data points is not generalizing to the pattern of the entire data. And in fact, the data set itself is some form of an exponential function that we're not capturing with this red plot or this red model that we created. So this is why we always need to think about what is the performance on the training data, and at the same time, what is the performance on unseen data sets, so that what was the original underlying distribution of this training data, that we want to make sure that any sample that you give me later that matches the distribution of the data that is underlying in my entire data set, I'm going to be able to have a comparable performance there as well. So in order for us to be able to talk about models performance on unseen data, we'll use some kind of a trick, and we'll say that since we don't have access to unseen data and we don't know what kind of data is going to come our way later on, what if I go ahead and segment my data set into 2 portions? One portion be training data that we'll use in order to fit the data and do model selection and all of those things. And then we'll use another segment. We don't touch it at all, and we basically use it as a test set, and we'll measure the model's performance on the kind of pseudo unseen data set using this test set that we have, which is kind of helping us to have some measurable performance of the model on unseen data in our case. So let's talk a little bit about let's talk more about this test set. So this test set that we're creating is nothing but a portion of our original data set. When we give you a data set for modeling, you will segment it into 2 portions, one training data that you'll use in order to fit the model, and then you will use the test data whenever your model is ready and whenever you want to test the performance of the model on the unseen data set. One thing that I want to note here is that we should only touch this test data only once. And the reason that we only touch it once is because we don't want to go back to the modeling process by using any information that we learned on the test data. Because otherwise our test data is not going to be the unseen data set that we wanted it to be. And technically the model is going to see it in some way. So that's why it's going to be only evaluated only once, and there is no notion or feedback from the performance of the model on the test data that can go back to the modeling process. So this testing only once as the external data set, external unseen data set is very important. So now we're making a change into our modeling pipeline. So in our modeling pipeline, our workflow now is going to be that I'm going to just get the data set, split it into training and test using train test split from sklearn, and then I'll basically use the training data for training, and I'll use the test data for just testing once I'm ready. If you're a visual person, this is exactly how it's going to work out. I have the training set in this blue box, and then I'm going to do a train test split. You'll decide about what portion of your data points are going to be allocated to training, what portion is going to be allocated to testing, and then you'll basically do a split, and you'll use one portion for training and one portion for testing. So we have training data and we have test data. I've been using the term training data when I was talking about linear regression, simple linear regression, and also OLS. But now you know where that term is coming from. This is like a portion of a data set that I'm just going to use in order to fit the model that I have. Let me move this for the sake of recording. All right, I think this is better. All right, let's see it in the code and see how it's going to work out. So we're going to work with the same data set that we had last time. We had vehicles data set. It had a bunch of different features. So I'm going to go ahead and load this data set. What you're seeing with this data set, actually, let me clear all these outputs and then restart. Okay, what you're seeing in this data frame is There is a column mile per gallon, or MPG, that I'm trying to predict. This is the target variable. And then there are a bunch of different features. But what we started doing last time was looking at the horsepower and using horsepower square, horsepower cube, and so on and so forth, in order to create all of those polynomial features. And the reason that we did that was because we were saying that as I go ahead and create higher orders of this feature, then technically I'm doing feature engineering, and technically my model is going to get more complex in that case. So what I'm going to do next is I'm going to create a data frame that has only the horsepower as the column for now, and then I'll keep adding all of those polynomial features for horsepower to the power of 2, to the power of 3, to the power of 4. And then I'm also creating my target vector or response vector y, which is now MPG. So remember that I said that now our workflow, instead of just directly using X and Y and fitting a linear regression model on X and Y, I want to do a train test split. And we said that there is a train test split function in sklearn that can that basically does that for us. So I'm going to basically call train test split, and I'll say that I have X and I have Y to split. Once you're splitting, you're exactly splitting the corresponding elements of X and Y, and you're putting them either in the training data or you're putting them in the test data, and they'll just move together. And that's why I'm passing both of them together in this case. There's also a bunch of different arguments that I want to show you what they are. One of them is called test size. And test size is nothing but a portion of the data set that you want to allocate to testing. Remember the schematic view that I showed you in this slide, that you saw that a smaller portion of the data set is allocated to testing because it's just going to be seen once. The size of the test set should only be some size that is reasonable, so that with those data points, you can capture the distribution or the general trend in the data set. Other than that, the size of the size of the test set is not that much of a concern. But what you need to be concerned about is having a reasonable size of the training data so that you can do the modeling process more effectively. So that's why in this case, I would say that I want to use 20% of my data set to be in my test data, and the rest of the 80% is going to be in the training data. This is about the right portion that you want to put in the test data. Anywhere between 10% or 20% can be a reasonable number, but definitely test sets should be way smaller than the training set that you're using because of the purposes that we're using training set and the test set for different kinds of tests. I'm going to also tell you something about shuffle. So there is the shuffle argument, that this shuffle argument by default is going to have a value of true. So I could just not have that there, but I'm showing it to you because it's very important for us to shuffle the data set before splitting into training and test, so that if the data is sorted in some way, you are not going to create a biased test set and a biased training set in any order. So you want to shuffle it first and then do the allocation. And because we are randomly allocating points into training and test with 20% probability that the data point is going to land into the test set and 80% that is going to land in the training set, we can also say that I'm defining a random state. You're defining some random seed that every time that you're running this code, you're going to be able to get exactly the same training data and exactly the same test data. This is for being able to reproduce exactly the same result that we are seeing right now every time that you run the model. Otherwise, if you don't define a seed every time that you run, it's going to be a different training set and a different test set. But the only criteria that you can enforce is that your test set has to be 20%. So let's take a look at what the output is going to look like. It looks like that I got a data frame. Here you're seeing the row labels, so 72, 89, and so on and so forth. And I have all of those features. And it is telling me that I have 313 rows or samples. Then there's also another data frame, and it tells me that I have 79 rows. This right here should tell you that I was able to just split my X into two portions. My design matrix is now divided into two portions. One has 313 samples, one has 79 samples. But it goes beyond that. It basically also does exactly the same allocation to the labels as well. So you're seeing that here, the first label series object here has a row of 72 and 89, which corresponds to exactly those row labels that we had in the first design, sub-design matrix that it was giving us. And also the same thing for a smaller set. So there we have 79 response values that are stored in this second series object. So technically it was giving me 4 things, and I wanted 4 things. I wanted to have the smaller design matrix for my training data. I wanted to have a small design matrix for a small matrix for my test data, and then the same thing for those response variables. So what if I go ahead and say that I'm going to assume that the first one that you gave me is X-train. The second one that you gave me was X-test, because these are the 2 data frames that I got. And then also Y-train and also Y-test, and I'll reallocate it. And what we're doing next is just checking the shape. So notice that I had 392 samples initially in the initial data frame, but then I split it into 80-20, 80% for training and 20% for test. And that's basically what I got. So now I have training and test split. Now, the next phase of the modeling is that I'm going to go ahead, take a look at my training data and use the training data to fit a model. So what I'm going to do is I'm going to go ahead and say that, go ahead and now create this model object and give me a linear regression object here. And then I'm going to fit only using my training data and my training labels, right? And this will basically just look at the training portion, the 313 sample, in order to create this linear regression object and find the model parameter. And what I can do later is I can go ahead and calculate the training error on the by calculating mean squared error on the training set, and also do the same thing for the test set. And I'm going to take a look at the result. So you see the training error is 18. The test error is 21, which is kind of expected. They're close to each other because of the way that I sampled. The distribution of the test data is similar to the distribution of the training because it's randomly splitted. And then on the other hand, the training error is slightly lower because what's happening there is that my model was able to see the training data, and it was able to optimize based on the training data, but it wasn't able to optimize exactly for all of the data points in the test data. So it's expected that generally the test error is going to be slightly higher. All right. Moving on, we also need to have another segment. And let me give you a motivation about why we need to have a third segment. So right now we have only 2 segments. The issue is I told you that you can only use the test data only once. What if I wasn't happy with the performance of the model on the test data? So in the previous example, I was getting root mean square error or mean square error of 21. What if I'm not happy with that? But if I want to reduce that error? So in that case, I can't go back and redo the modeling because we said that the test data has to be only used once. So in this case, what we're going to say is that we're going to use exactly the same trick one more time. If you want to have some internal test set so that you can use that test set to go around this modeling cycle and keep refining your modeling and keep, for example, updating the hyperparameter and keep doing more feature engineering, let me give you an internal test set that I'm calling it validation set. So you can use that for internal testing. And then once you're satisfied with the performance of the model on the internal test set, which is the validation set, then ship the model, then only test on the test set only once. And hopefully by 2 kind of layers of testing, now you're going to be satisfied with the performance that you're going to get on the test data. So technically, again, the modeling process is going to be a cycle that's going to happen between the training data, and you're using the training data for training the model, and you're using the validation set in order to adjust the model and repeat the modeling process. And then once you're done, then you're going to go ahead and test the performance of the model on the external test set that is going to be only tested once. So our entire breakdown is now going to be that now we're moving from the 2 segments of training set and the test set, And we're going to say that, okay, I'm going to set aside a portion of the training set for my internal testing, and I'm going to call that validation set. And this is going to be the new kind of set of, the new set of data points that we need to have for our modeling process. So let me do that in the code here for you. So I'm going to, let me, for the sake of time, to just go ahead and get this line. And I'm just going to say that I'm using exactly the same thing, but this time I'm splitting my training data, right? Using the same 20% portion for the validation set. It's called test size because that's the argument name. But technically what it does is it's going to set aside 20% for you. And then what I'm getting as a result is going to be X train mini. I'm going to say that it's going to give me now X validation because that is smaller portion this time is my validation data. And I'm going to say that, okay, now I have Y train mini and then I have Y validation. And then technically what I can do is testing it one more time. 313 was my original training set size. Now my mini training size is 250, and then 20% of that is used for validation. So what I want to show you here is why this validation data is very helpful. So let me run this and explain what's happening here. So what I plotted in this case is that I went ahead, used the mini training data. Let me show you here, this mini training data. And I said that let's go ahead and fit different models of different complexity. You see when I'm iterating over order, that's the degree of the polynomial. So I say that, what if the degree of the polynomial is 2, 3, and 4? I'm using the mini training data in order to fit the polynomial of degree 2, 3, and 4. And then what I'm reporting here is how the model is fitting to the training data. And then I'm also annotating there that the validation error for each one of those models is what? That's the validation mean squared error. So you can see that the fit is kind of similar for all of those models, but you're seeing that the validation MSE keeps decreasing as I increase the model complexity. So this will give you a sense that degree 4 polynomial is not so bad for this data set because you have a good performance on the training data, and then at the same time, you're not overfitting to the training data, and your performance on the validation set, internal set, is still good. This is what's called model selection. Using the validation set, I'm deciding which order of the polynomial is more appropriate, what features I want to include. And once I conclude that kind of decision based on the result that I'm seeing on the validation data, then I'll go ahead and do the modeling one more time and then test it on the test set. This is why this validation set is very important for the model selection process. I can go to the next level and actually get crazy and say that I want to explore all degrees of polynomials between 0 and 17 and including 17, right? Let me just keep increasing it, and then you tell me what's the performance of the model on the validation set. And then what I'm seeing is, as I keep increasing the model complexity, I want to see what the trend is going to look like. So what I'm doing exactly is, again, iterating over all of those degrees that I want, and then I'm calling this function fit model dataset, which technically is a pipeline function that all it does is it goes ahead and gets the feature that I have, and then it goes ahead and create all of those polynomial features. This is also what you have seen in the feature engineering lecture, that I can just call this polynomial feature and it will create the different degrees of polynomial of that feature. And in this case, my feature is only horsepower. So it's going to be horsepower, horsepower squared, and so on and so forth. So I'm going to go ahead and run this. And what you're seeing in this plot is that as model complexity increases, starting from 0 all the way to 17, you're seeing the plotted value is the validation error. So you see validation error keeps decreasing. And those validation errors that you saw in the previous plot between 2, 3, and 4, that's kind of the flat line that you're seeing in this plot. So as I keep increasing the model complexity, then what I'm seeing is, first I'm seeing, what's happening here? I'm seeing a decline. And then after a certain point, then I'm seeing an increase in the model error. So what you're seeing is that as you keep increasing the model complexity at a certain point, then you're not going to fit to the general trend of the data, and you will start actually overfitting to the test data, to the training data. So what we can do also in addition to that is I can go ahead and take a look at all of these MSCs so that I don't visually take a look at them, but I can basically look at all of these MSC values and then figure out which MSC value is the smallest and use the smallest MSC value as the degree of the polynomial that I want to use at the end. I can actually go ahead and take a look at the index, and it's telling me that degree polynomial 8 has the minimum MSC on the validation set. After 8, it will keep increasing. And I don't want that to happen because that shows that I was overfitting to the training data in that case. What I'm doing next is just adding all of those features that were missing from my design matrix, because my design matrix had all the features all to the degree of 4. Now I'm adding 5, 6, 7, and 8 so that my features are degree 8 polynomial. And what I'm doing next is technically just doing, just fitting on the entire training data. This is not on the mini training data. You use the portion of the training data to make an informed decision about the degree of the polynomial, right? And you were using the X-train mini in order to fit the model, or fit model parameters to different kind of degree of the polynomial. But once you made that decision, you'll put them back into one training set. You will go ahead and train the model, fit the model, and then you will technically take a look at its performance on the test data. This is the final thing that you put everything together because the more data that you have, the better model you can get. You combine them, you fit the model, and then your model is ready to be shipped, and then you will ship it and you test it on the test data, which in this case is telling us that the root mean squared error is 20, which is even better than the previous 21 that we got. If I scroll up, you will see that if I didn't have this kind of fancy way of doing all of these calculations, what I was getting was 18 was my training error and the test error was 21. Now I was able to bring it down a little bit further by just going around this cycle, trying multiple things, doing model selection, and now the model is looking a little bit better on the test data. Question? So your question, the question is, can we, could we use the entire data set initially, all the training data, without splitting into the training mini and the validation to do this? I wasn't able to do that because once you are at this stage, right? Once you do the modeling and the entire training data, your only choice is to test on the test data only once. And now when you see 21, you can't go back and change anything, right? If you go back and change something in your modeling process and like keep changing the degree of the polynomial, then your test set is not going to be an unbiased, unseen data set towards your entire modeling pipeline. It needs to be entirely isolated. So nothing about that should be incorporated into your modeling process. That's why I couldn't use that. That's why it's not a one-shot thing. If you want to make it multiple shots, you need to have your internal testing, which is what I replicated in the validation set. I used the validation set as internal testing to make the selection between all different combinations of the model. But once I was ready and once I made that decision, I put them back together, I fit the model, and then I tested it on the test data. Very good question. Question. We will get to that. The question was, as the model complexity increases, is it always the case that the training error decreases and the test error sometimes decreases, sometimes doesn't? That's generally correct, but we'll take a look at that more carefully. Okay, so let's take a look. So this is what we had seen. And technically, if I put this plot together with the previous plot that you had seen, then we would get something like this, that the training error was decreasing, the variance was increasing as I increased the model complexity, and the validation error was something that was decreasing and then it was increasing. So generally speaking, yes, as the model complexity increases, the training error is going to decrease. That's generally correct. There might be cases that your data is structured in a certain way that as you keep increasing it after a certain point, your model, your training error might not necessarily decrease and might flat out after a certain point. The variance generally increases, and then the error on the validation set first decreases and then increases. And the point that we're interested in is actually finding that sweet spot in the middle of underfitting, that before it, when the model performance on the validation set is still decreasing. That means that there is still capacity in the model to learn better, and then to keep decreasing that validation error. But after a certain point, as you increase the model complexity, then the validation error is going to increase. That shows a sign of overfitting. So you are overfitting to the training data, and that's why you're not capturing the trend in the validation set that much. And again, what we're interested in is just, again, finding that sweet spot in the middle by controlling the model complexity, which is what we're going to see in the second half of today's lecture. Before we move on to the second half, I want to talk about k-fold cross-validation. K-fold cross-validation is something that you'll use in your project A2, the next phase of project, really deeply, and it's going to be a very practical technique that you'll learn. And to motivate why we need to have k-fold cross-validation, I also want to show you that when I was extracting this validation set, it was only one time or one chunk that I was extracting from my data, and I was treating that as a validation set. So it was possible that the way that I was separating that validation set was kind of going to be biased in a certain way. So when I was making a model selection based on that only one validation set, I might make a biased decision. So in practice, if I go ahead and randomly select different types of validation sets using different seeds, and take a look at what the training validation MSC is going to be, the validation error can be like 14, 24, and 22. So you can see that the choice of the validation set is going to really give you different types of performances, and that's why it can, in some cases, make your training process biased. So what we're going to do is, instead of only relying on one validation set, we're going to say that, okay, the entire modeling process is based on the entire training data, right? This is the entire training data. You're extracting one portion and you're treating that as validation set. What if you just take a look at multiple different possibilities for validation set, so that you consider multiple different models and multiple different validation sets in order to make a decision about your model selection, about hyperparameter selection, and so on and so forth, instead of relying on one data set or one validation set that can make you biased. The way that it's going to work out is, I would say that, okay, I wanted to give you only 20% of my data to be the validation, and the rest of the training data, 80% of the training data, be used as the mini training or the actual training data. What I can say is that if I wanted to treat and only use 20%, there are different 20% chunks in my data set. So what I can do is I can go ahead and say that, okay, what if I use the validation, the first 20% for my validation and the rest for my training? What if I use the second 20% as my validation and the rest for training, and so on and so forth? So there are 5 different 20% chunks of non-overlapping data points that I can use for validation. And technically what I can do is I can technically have any data point to be part of the validation at least once, or exactly once. And this is exactly going to do that. What I'm going to do is I'm going to do a modeling based on each one of those segmentations, each one of those training data. I'll evaluate the performance on the specific validation data. I'll do exactly the same thing for all of those different chunks. Each one of them is going to give me a different model. Each one of them is going to have a different validation set. Each one of them is going to have a different performance. And when I want to decide whether degree 4 polynomial is better or degree 5 polynomial is better, I can take a look at the average of the performance of degree 4 over all of those models and the average of degree 5 over all of those models. And then I'll make a decision. This way, my modeling is going to be more robust and it's less likely for it to be biased in any way. So let's reiterate what's happening. The chunk that I'm saying that I want to use it for validation is called validation fold, right? When I say that I want to use 20% for validation, that means that I have to divide my data set into 5 folds. Each time I'll take one fold. That is going to be my validation. I'm using the rest of the 4 folds for the training. And then this whole process is called cross-validation. That depends on those fold allocations, and then each fold is going to be the validation set only once. And then each fold is going to exactly be the validation exactly once. So what do I mean by K-fold cross-validation? Because that's the name of the algorithm or the process that we talked about. When I say that I want to split it, have a 20% validation split, and I said that that basically means that I'll have 5 different folds of 20% in my data, because 5 times 20% is going to be 100%, and that covers the entire data set. That technically means that I'm running a 5-fold cross-validation. So K refers to the number of folds that you want to create in your data set. So the way that the algorithm works is that you will decide about K ahead of time. K is a hyperparameter, similar to learning rate. I'll decide about the number of folds. I'll say that for a given K value, in our case, it was 5. I'm going to divide the data set into K folds. I'll pick 1 fold for validation. So this is 1 fold only for validation. Then I'll use the rest of the data, the rest of the other folds as my testing, as my training. Other folds are going to be my training data points. And then what I'll do is, once I fit the model and the training data, I will evaluate the model's performance on the validation fold. So here I'm going to say that we're computing the model's error on the validation fold, which is exactly the fold that we first decided and segmented out from the process. So still you can see that the model was trained on all the folds other than the validation. So still it's valid that the validation is my internal testing. So what I'll do next is I will repeat the exact same thing for all of the K folds. Each one of those K folds is going to be my validation once. Each one of them is going to create, for each one of those kind of iterations, I'm going to have a model. I'm going to have a model performance. And then what I'm going to report at the end is that the cross-validation error is equal to the average of the error that I have from all of those K models and K different folds of validation that I had, instead of only be based on one validation fold. So again, this makes the modeling process more robust. So let's see how that works. Let's assume that I'm going with the same 5-fold cross-validation. What I'll do is I will use I'll divide the data set into 5 folds. I'll use one of those folds here for the validation, and I'll use the rest for testing, for training. So I'll train on the lighter blue portion, and then I'll report the MSD on the darker blue portion, or the validation fold that I have. Then I'll keep remembering this validation error that I got. I'll do exactly the same thing for all of the other 4 folds. Each one of them is going to give me 4 models. Each one of them is going to give me a validation error on the respective validation fold. And what I'll do at the end is the cross-validation error is equal to the average of all of those validation errors that you saw. So on average, we'll say that if you make a decision certain way, if I'm talking about only including degree 4 polynomial versus degree 5 polynomial, the validation error for 4 is equal to whatever, the validation error for 5 is this other number, and then we compare those cross-validation errors in order to make a decision between the 2 options that we have. So let's take a look at this workflow. So the entire data set that we had, initially we said that we're splitting into training and test. Then we said that, okay, we're gonna split the training set into the mini training or training and the validation. But then we said that, okay, one split is not enough. It might be biased. Let's do k-fold cross-validation. Let's divide it into k segments, have k different processes or k different options for the validation set. And then technically we're doing more computation, but it will come at the benefit of the modeling process being more robust. Again. So why do we need to use this? I talked about the model selection. So if you have multiple options, if you have features that you want to tune, you might want to decide about something in your modeling process. We use cross-validation for that. We are also using it for hyperparameter tuning or deciding about hyperparameters. And we kept talking about hyperparameters before without formally defining it. I'm super happy that now we're finally to the point that I can explain what hyperparameter is, because now we know what parameters are. Hyperparameters are the things that we need to decide about ahead of the modeling process. So what are those examples? The example could be the degree of the polynomial that you need to decide beforehand. There is no way that you can have OLS or gradient descent to be able to tell you what the degree of the polynomial you should use. Once you put in all of your features into the model, it's going to use all of them. It's not going to do selection for you. Specifically, OLS is not going to do that for you. Learning rate. Remember, learning rate in the gradient descent algorithm was a decision that we had to make ahead of time. We said that there is like a balance that you don't want to have a learning rate that's too small or too large, and there were issues with each one of them. But you can have multiple options that you need to pick, but you need to decide about which learning rate is going to give you the optimum result at the end. There's also this regularization penalty that you haven't seen yet, but we're going to see that in the second half of today's lecture, which is going to be a few slides from now. So let's take a look at how it can actually be done. For hyperparameter tuning, we use cross-validation, k-fold cross-validation. And what we can do is we can decide about the set of guesses or a set of options we have. In the case of the degree of the polynomial, I had the options of 0 up until 17, right? Those were my options or my guesses. Same can be true for learning rate and can be true for other hyperparameters that you want to tune. You look at all of those guesses that you have. For each one of those guesses, you run k-fold cross-validation. Now you have cross-validation error at the end. So each one of those choices is going to give you a value. And what you'll do at the end is you will select the hyperparameter that gives you the lowest cross-validation error. And that's a simple decision. What do you do next? You combine everything together. Now you have a decision about your hyperparameter. You fit the model and the training data using that hyperparameter decision that you already made, and then just test it once on the test data, right? This is the entire pipeline that we'll have. Let's take a look at one example. So let's say that I have a learning rate. Let's say that I'm investigating options of learning rate being 0.1, being 1, or being 10. And I want to go with threefold cross-validation. Again, the choice of K for K-fold is just your decision. It's the hyperparameter that you're choosing. So here in this case, I'm choosing 3. I could choose 7. I could choose 5, whatever number that I want. But the process that I outlined there means that I have to run one full cross-validation on every option of these guesses that I have. So meaning that I'm going to, for learning rate of 0.1, run full cross-validation. So that means that I have to consider 3 different validation folds, have 3 different models, calculate those MSEs for those 3 different models, and then I'm calculating the average of all of those errors, and that's my cross-validation error. I'll do exactly the same thing for alpha equal to 1 and alpha equal to 10. And then the decision that I'll make at the end is I'll compare all of those numbers. Which one is the smallest? Alpha of 0.1 is the smallest. And then I will select 0.1. That's a part of hyperparameter selection, or part of the model selection process that I can technically do using cross-validation. Again, this technique is very important in practice when you're doing projects, because you're not going to have access to our own test data, and you will only be able to use the test data on Gradoscope only a few times a day. So it is very important for you to do cross-validation, to have a sense of how your model is going to perform on a pseudo unseen data, and then do all of these selections of the hyperparameters accurately so that your model performs well overall when you're submitting it to Gradoscope. So first slide of the day. Which one of these alphas should I choose? Alpha, there are multiple different alphas. There's a still threefold cross-validation. I shouldn't have advanced it, but that's a free question for you there. All right, can someone explain to the class why 0.1 is the right choice? I'll take a volunteer from here. Do you want to make a guess? Yep. It has the lowest cross-validation error. Yes, for 0.1, the error, the cross-validation error, which is the average of all of those errors, is equal to 4.67, and that's the smallest across all of those cross-validation errors that we had seen. So let's get more practice. So this is a question that I'm saying that I want to run k-fold cross-validation with k equal to 3. And I have 4 possible hyperparameters that I want to choose for the learning rate. Options are 0.01, 0.11, and 10. How many total MSE values do I need to compute to get the quality of alpha equal to 10? This is a careful reading question. I like the option of at least one, because you'll at least calculate it once. That's true. Okay, so let me read that one more time. K is equal to 3. So every time that I want to run the cross-validation, I am dividing it into 3 different scenarios because there are 3 different folds there, right? So for every option, for every guess, there are 3 MSE values that I am calculating for, so I'm training on anything but that validation fold, and then I'm testing, calculating the MSE on that specific validation fold. So technically, because my option is only alpha equal to 10, there is one cross-validation that I'm running. And for that cross-validation, because k is equal to 3, there are 3 different models, and there are 3 different MSEs that I just need to calculate. So the right answer, unfortunately, is that the small, tiny tree over there. Okay? But if the question was this question, that the question says that, okay, I want to do I want to do four-fold cross-validation, but I have 5 options for a hyperparameter. It doesn't matter what those options are. How many MSEs do you need to calculate in this case? Okay, so 20. Yes, 20. 5 times 4. That's easy, right? There's no trick. Each time for every guess, you have to calculate or train 5 different models for 4 different models, and then calculate 4 different MSEs. You have 5 options, 5 times 4, 20. And that's simple. So first part is over. Now let's talk about the second part. We kept talking about the fact that as I keep increasing the model complexity, then the model might overfit to the training data. And then we were kind of using this cross-validation and the validation set in some way for us to have a sense of when we're overfitting to the training data. But there is a more kind of systematic way that we can also control the model complexity. And I'm going to walk you through what that is. So technically, again, we're focusing on this plot right here. I'm interested in this exact point that's going to give me a reasonable performance on the training data, a reasonable performance on the test data, but at the same time, it's not underfitting or overfitting on the validation data set as well. So remember when I was talking about model complexity, I kept saying that, Okay, if the number of features keeps increasing, generally the complexity increases. So this is as if what I'm interested in is making sure that some of those parameters that are associated to those features is equal to 0. So it cancels out that feature entirely, right? So that's what I was interested in. But instead of me actually going ahead and doing that, I can soften that assumption and I can say that, okay, include all of the features that you did feature engineering and you included there, but pick only a little bit of each one of those features. So the idea is that we just want to make sure that each individual feature is not heavily driving the entire decision in our modeling. Because what's happening here is that my prediction is happening based on the summation of all of these terms. What we want is we want to have kind of comparable contribution of all of the features that are going to be relevant to the target value. And that's why we don't want to have large weights associated with some features. And we just want to make sure that the magnitudes of all of these parameters is controlled. So what do I mean by that? What I mean is every time that I'm controlling these magnitudes of these features, in a way, I'm trying to derive them as close as possible to 0. When those parameters are derived to 0, this is as if that feature is entirely removed, right? If the value of the feature, if the value of the parameter is not close to 0, and the value of the parameter is very small, it can still influence the final decision, but its impact is going to be less. So that less impact is still going to make the model less complex compared to the case that there's going to be multiple competing factors and a very high dimensional function that I'm trying to fit into the training data that I have. So this idea is called regularization. You're technically assuming that you want to put some limit on the magnitude of these parameters. And why do I talk about magnitudes? Because what I want to do is I want to make sure that these values, regardless of whether they're positive or negative, I want to make sure that they're close to 0 and they're small so that they're not going to compete and heavily influence the final decision. So I'm going to highlight this piece because it is super important to me. This regularization idea means that we want to restrict the complexity by putting a limit on the magnitudes of the model parameter. So how do we do that? It sounds like there is some magnitude going on that we can measure by absolute value. And then for limiting, there should be some inequality that I can create. And technically, I can write this condition by this inequality. I can say that I have a budget of Q, and I'm telling all of the model parameters that go ahead and divide this budget amongst yourselves in a way that the absolute value of the summation of all of these parameters do not exceed the budget that I'm allocating. So in a way, I'm trying to restrict all of those features. And during the modeling process, I'm going to be able to use this condition in order to make sure that only the features that are super relevant or super correlated with the final estimation are going to be utilized. And then the ones that are not super relevant, they're not going to be contributing, and they're going to be values close to 0 so that they don't use that much of the budget, total budget that we have. So I'm going to highlight this Q as this limit that we're putting. And then I'm highlighting these magnitudes because we're doing the summation on the magnitudes of these parameters of the model that we have. So it seems kind of simple. So there is this budget thing, there's all of these parameters, and I'm just making sure that the summation of all of these parameters, the magnitudes of these parameters do not exceed the theta parameter, and they are going to do the competing in the modeling process so that we see which one of those features are winners, and they're going to be incorporated into the final kind of prediction, and which one of them are going to be driving to 0. One thing that I want to note here is that we do not regularize on theta 0 or bias term. This is because if there is a baseline that needs to be corrected in the training data, we don't want to penalize model to use all of its budget to fix the baseline. The baseline is not going to be considered as increasing or decreasing the model complexity. If my intercept is 100 versus 10 to the 4 or whatever, the model complexity is still not going to change. The model complexity is influenced by the number of features and the complexity of those features. That's why we do not regularize on theta 0. And that's also why this I starts from 1 instead of starting from 0. So that's kind of a very kind of test question that you should also remember. So let me visually tell you how this budget thing is working out. So I have this gradient descent landscape that you learned from the gradient descent lecture. Think about it as a bowl, that what I'm interested in, getting into the center of this bowl, or that dark blue area that has the minimum mean squared error, right? So around in the center, the mean squared error is small. And as I move away from it, the mean squared error or the cost is going to increase. So in the cost landscape, in the gradient descent lecture, you learned that for every combination of theta I values, here I'm just assuming that I have two features and I only have theta 1 and theta 2. For every combination of them, there is a loss value that you're observing. What we're interested in gradient descent is to find out where the optimum parameter is, or where is the combination of theta 1 and theta 2 that gives us the minimum loss value, which is what you're seeing at the center there, that if I don't have any regularization or if I don't put any penalty, with gradient descent, we're hopeful that if the function is convex, we'll be able to find the minimum possible value for the loss function. But what happens if I go ahead and say that, okay, I now have this condition that you have to satisfy? Not only that we're looking at having the minimum or the darkest area in this function, but that I also want to make sure that there is this additional condition that needs to be satisfied, that the absolute value of the theta i's should be less than the budget Q. If it makes it easier for you to think about Q as a concrete number, you can think about Q as being 10. Let's think about the case that your budget is 10. You just want to make sure that the summation of these absolute values is less than or equal to 10. So what that condition or constraint looks like is this diamond area. What is this diamond area? This diamond area basically says that, okay, at this region is the point that theta 1 is equal to Q, and then theta 2 is equal to 0, right? At this other corner, then your theta 2 is equal to Q, and your theta 1 is equal to 0. And then you can kind of see that inside this diamond is the area that my condition is satisfied. But at the same time, I'm also operating on this entire landscape. And what I'm interested in is finding the darkest area, which represents the minimum loss function in the entire training data that is within this diamond, which technically is going to be this point on the edge, on the corner of this diamond shape. So this is the case that with the budget of Q, in this case, I was able to find the minimum or the best theta parameter that is satisfying the condition, as well as it's giving me the minimum error compared to any other thing that existed inside this diamond thing that I had. Okay. One thing to notice here is that my optimum point was at the corner, right? This is the point that theta 2 is equal to Q and theta 1 is equal to 0. This is exactly the case that the parameter 1 and the feature 1 is entirely going to be removed from your modeling. So with this way of regularization, your model decided that, okay, I can just satisfy this condition and obtain the minimum error possible within this condition by just eliminating feature 1 and focusing on feature 2 and just relying on feature 2 to do the prediction for us. And in a sense, it does the feature selection for us. So let's now talk about the notion of this Q and what happens when Q is small versus the Q is large. When I have a smaller Q, then technically this means that my diamond is smaller. My diamond is always going to be around the origin, right? And when Q is smaller, that means that I'm further away from the optimum point that I can be. So the optimum setup, the optimum parameter based on this condition is going to be not so ideal, and it's going to be slightly different from the optimum place that I can be. So the quality of the model is going to be less, obviously, but at the same time, you are now constraining your model to be not so complicated. When I have a large Q, what happens is that the the diamond is going to have more intersection with the good regions that you have, and it's more likely that the optimum point is going to be this time closer to the case that you had no regularization. So think about this budget thing as a limiting factor, but at the same time, the model itself is going to find a way to be as close as possible to the optimum point that it can, to the extent that it does not violate the condition that we put in place. So let's think about these options. We're thinking about how to budget and what is the right budget for our model. And this is, again, a hyperparameter that we need to decide. What should be the size of this diamond? So the question is, how does the size of Q or budget relates to model complexity? Do you think that the model is going to be more complex when budget is larger or less complex? Yeah. So the question is that if the data is normalized, which we're going to talk about that shortly, do we still want to regularize on theta zero? The answer is still yes, because depending on your hyperparameter, even if you're actually, no, in that case, you don't need to have an intercept, right? So if you don't have an intercept, then technically it's the same thing, right? So you are not regularizing it because it doesn't exist, right? Good question, tricky question. All right, so is there anyone in the center that wants to tell us why the correct choice is the first option? Any volunteer? Sure. So if I have a small q, that means that the parameters are going to be smaller, right? When the parameters are smaller, then it's likely that some of them are close to zero. That leads to less model complexity, right? And also it removes the impact of a huge impact of all of the parameters when all of the features when the parameters are small. So small q corresponds to a simpler model, and a large q refers to a more complex model, because what's happening is that, again, when your Q is going to become larger and larger and larger, at a certain point, technically it's large enough that you remove the entire constraint, right? So what's happening is if I keep increasing this diamond, it will include my optimum point at a certain point. So I'm not going to be able to use this condition in order to do any regularization or any limiting of the scope of the parameters that I have. So then I have two more slide questions. These are really kind of insightful for you to get a sense of what this regularization is all about. The question is, if we pick a very large value, what kind of model will you have? Will you have a model that only returns zero, a constant model, OLS, or something else that's not listed? So Q is very large. Think about what's happening in that case. Q very large means OLS. So the optimum solution that you'll get is going to be the optimum point within this condition that you have. And when your diamond is large, you're basically including this optimum solution that you had originally. So there is no regularization. So this is as if you've done nothing, and there is no regularization. So at the end, you will have the OLS technically happening there. What happens when Q is small? So think about the diamond getting smaller and smaller. Is it going to give all zeros? Is it going to be still OLS? Who says constant model? Constant model. Why is it a constant model? what happens if Q is 0? It's small, very. Exactly. So when Q is very small, let's think about the extreme case that it's equal to 0. Then all of those parameters, they have to be 0 because my diamond technically is just the origin. Everything really needs to be at the origin. So all of the Q values has to be equal to 0. All of the theta values has to be equal to 0. And what happens is the only thing that I'll be left with is my theta 0 because I didn't regularize on theta 0. So it's going to give me a constant model, a very simple model that with heavy regularization, we can obtain that. Who says that it's going to return 0? Yes, why? The theta values are going to be 0, but the model does not necessarily give 0, and it will give 0 if there is no bias term. So if your model doesn't have a bias term, there is no theta 0, so you're just returning theta 0 because that's the only non-zero or non-regularized thing that you have. And if you don't happen to have the bias term, that's technically what's happening there. So both of those options are correct. In case of no intercept, the model is going to constantly give 0. This is with heavy regularization, meaning that you'll have a comparable performance across the training data and across the validation with no overfitting, but there is a high underfitting that you have in both of the cases with 0 and also with the constant model. So there is this kind of balance that we're trying to play here, that what is the right size of this diamond thing? And the good news is that what I can do is I can throw in some linear algebra at you without any proof to show you that there is actually a way that we can optimize the model by considering this condition and just have the modeling framework that we have to do that for us. So technically, this was my condition. I just wanted to make sure that the sum of these absolute values is less than or equal to Q. But at the same time, my main objective function was to minimize mean squared error. So how do I combine these two together? I will combine these two together using this condition that I'm doing L1 regularization on the theta vector. Remember the notion of L1 loss that we had before? The condition that you see on the right-hand side is exactly L1. That's taking L1 or L1 norm of the theta vector. So what I'm trying to do is I'm trying to combine these two terms together. One is my main objective function, and one is a constraint or a condition that I have that I need to combine these two together. But because we don't know how we can combine them together into the training framework, we'll use a concept that's called Lagrangian duality, which you will learn in EECS 127 if you want to take it later on, or if you've taken it. This is a concept that's going to be familiar to you. Every time that we have an objective function with a constraint, we can combine them by, in this format, we can combine them by introducing a hyperparameter or a weight factor for the condition term. So we would say that what we're interested in is to make sure that my model MSC is going to be calculated. So this is mean squared error. So this is the mean squared error that's happening here. And then I'm saying that the condition that I said that I need to satisfy is this budget thing or this L1 norm. And I'm going to assign a weight or this lambda parameter in order to play a balance between the objective function and the condition that I have. So in reality, what's happening there is that I'm not going to enforce budget anymore, but I'm saying that if you need to spend more budget, use more budget. But then it will come also at the cost that then the error is going to be also larger in those cases. So there's always going to be a balance between these two terms that are going to compete with each other. So this is going to be our new objective function. The first part of the objective function is going to try to keep the mean squared error small. So it tries to fit the model to the training data as much as possible or as well as possible. And then the second term is going to try to make sure that the complexity of the model is going to be controlled. So if you technically go ahead and increase this complexity by a lot, by having very large theta I values, your entire objective function is going to be increased in value. So if your goal is to minimize this objective function, you need to minimize those parts. So this is a very important factor. So then kind of the notion of what happened with the budget thing here technically means that if this lambda value is a large value, we need to pay more attention to the second term versus when the lambda value is a small value, we don't need to be concerned with the second term that much. So in the case that lambda is equal to 0, it will entirely eliminate the second term. And this is as if you have the normal OLS. So this, you can think about this lambda as inverse of your budget. So if your budget was large, then technically that meant that you wanted to have a very complex model. How do you do that? You need to have a very small lambda. So this is a hyperparameter that we need to decide ahead of time to just say that how much do we want to really regularize? If you don't care about regularization, set it to be 0 or a value close to 0. This means that my parameter when lambda is equal to 0, this is as if Q is close to infinity. So this is a very large diamond that we had that we saw that was an OLS. In a case that we want to really heavily regularize, we'll have a very large or substantially large lambda value, which is equal to having a small budget. 1 over Q is going to be large, with Q being a small value. How do we decide about the right value or right amount of regularization so that you don't do underfitting, you don't do overfitting, because these two terms are technically controlling underfitting versus overfitting. We do cross-validation. This is a hyperparameter that I introduced a few slides ago, and I said that there will be a way for us to decide about it and decide about how much regularization we want to do. So this regularization that we did with L1 regularization is called LASSO regression. LASSO stands for least absolute shrinkage and selection operator, because it does shrink the parameters. And then we saw that it will also do the selection for us as well, because most of the time the optimum is going to be at the corners, and at the corners is the time that you have one or more of the parameters equal to 0. So in a sense, you are doing the selection of the parameters as well. So how do we do this in practice? You know the kind of the math behind it, but actual practical use of it is going to be very simple. From the same linear model framework that we had, instead of just calling linear regression, here you're calling LASSO. And LASSO in practice is linear regression with L1 regularization. That's what we just saw. The only parameter that you need to pass here is your lambda. So this alpha equal to 1, alpha stands for this, or is in place for the lambda concept that we saw in the equation. So this technically means that just assign lambda to be equal to 1, just fit the linear regression model with the L1 regularization, or create that object, and then we're fitting it on the training data, and then we're taking a look at the coefficients. This is exactly the same pipeline that we had before, but now you know that there is a systematic way of us enforcing the model complexity to be as small as possible. What you're seeing here is all of these model coefficients, a lot of them are very small parameters. So although it was a highly complex model with 8 different features or 9 different features, then some of these parameters are small. And this basically means that they're not driving the decision that much. There is a small caveat here, or actually, sorry, this is the part that I already mentioned, that because these are small, this is kind of technically thinking that it will do the feature selection for us. So it will LASSO regression both reduces the size of those parameters and the significance of each one of those features that we have, and at the same time, it can also perform as the selection operator for us as well. One thing that I want to talk about is the impact or the importance of the data standardization or normalization. So what I want you to see is this horsepower thing that I was creating, horsepower score, and then all the way to the power of 8. The magnitude of these features are different. When I was talking about these parameters here, and I was saying that, oh, these values are very small, my notion of very small, and that's why they don't have that much influence, was a little bit flawed, because those small values are going to be multiplied by these very large values, and they can still drive some kind of decision in the model. So what we just want to make sure that we do is we just need to make sure that the magnitudes of the features are the same, so that those features that are substantially different in magnitudes are not competing with each other when there is like a fixed budget that needs to be allocated amongst all of them. So technically what's happening is with the horsepower to the power of 8 and then the horsepower itself, if you just look at the first data point, and the first data point had the horsepower value be 150, when you take 150 to the power of 8, you're getting this very large value. And then technically what you're seeing is that those weights that are allocated to horsepower feature and horsepower to the power of 8, they're going to be different. And for the feature of horsepower to be able to make any influence, it needs to use a substantial amount of the budget. So you see 0.1 as the 0.5 as the absolute value is substantially larger than this weight that this other feature has used. And that's why it's very important for us to remove that competition ahead of time by standardizing the data. And by standardization, what we mean is removing the baseline and then making sure that the standard deviation of all of those features are equal to 1. So this is kind of the z-score calculation that you had seen in data 8, that you calculate the average of a column, you calculate the standard deviation of a column or a feature, you just standardize the data by subtracting the mean and dividing it by a standard deviation. What happens if I do that? If I do that, and I now take a look at my X-train standardized, and I go ahead and just do the same LASSO regression with the same lambda to be equal to 1, what you're seeing is that a lot of those theta values are exactly equal to 0, because now all of those features are either contributing or not contributing. So you can directly see that now it's technically performing the selection for me. So some of those features are in my feature set, some of them aren't. And at the end, my model is less complex with those 4 or 5 features removed from my feature set. So every time that I talked about L1 norm, I also talked about L2 norm. So you might have guessed that L2 is coming your way as well. The concept is exactly the same, except for here we're saying that when I'm talking about the budget thing and the condition, instead of me looking at the magnitudes in terms of absolute values, I'm considering magnitudes as the scores of those parameters. This is exactly what we did with L1 loss and L2 loss. And what you're seeing is that my budget is now within this circle. And the equation for this circle is that the summation of theta I scores for all of those features is starting from 1 and not 0 all the way to P should be less than this budget thing that I have. The rest of the pipeline is exactly the same. What happens next? I have the objective function, and then I have this condition that I need to satisfy. I will use Lagrangian duality to combine them into one term. There is the term that makes sure that my MSC is low on the training data, and there is this second term that makes sure that the model is not complex, and they'll be competing to overall keep the summation of the two as small as possible. And this technically is going to be our new model. This linear regression with L2 regularization is called ridge regression. There's nothing fancy about ridge. It's a historical term. Just know that every time that you hear about ridge regression, it's just nothing but linear regression with this additional constraint that we're putting. If I want to implement it, the implementation is as simple as just calling dot ridge instead of dot linear regression or instead of dot LASSO. Here I'm just saying that dot ridge, and I just also need to pass the lambda parameter that I decide ahead of time as a hyperparameter. I will get that object, then I'm fitting it to the training data and the training labels, and then I can also take a look at the coefficients. If you take a look at the coefficients, some of them are small, some of them aren't so small. And this is just general performance of this ridge regression in this case. I want to say one last point in the last minute, and that's one of the main reasons that a lot of people might want to use ridge regression, regardless of whether they care about regularization or not. And the fact is that the ridge regression or linear regression with L2 regularization has a closed form solution. So as soon as you have your design matrix, as soon as you have your Y vector, and you know N as the number of samples, and you decide about your regularization parameter, there is a closed form solution for theta. What does that mean? This also means that regardless of whether your X is full column rank or not, this is still holds. So this is now much better than OLS. There's also one other important factor here is that regardless of your training data, if you're doing the ridge regression or if you're imposing L2 regularization, there will be a unique solution to your problem. This is very important because the unique solution is going to happen here. So this is the summary of everything. We've seen OLS before. We had seen today, we talked about LASSO regression. We talked about ridge regression. And this is going to be really practical in Project A2. I just want you to pay attention to all of the details of cross validation and regularization that we talked about today. And that was it for today. Thanks for coming.